So we covered hard margin SVM and soft margin SVM, support vector machine. Just I wanted to show you an example before we start the new topic. Okay, I have just this data set here. If you look at the size of X, it's 313 by 2. It's two-dimensional data, and we have 313 of them. So let me show you the form of this data. So I'm going to plot this is the data, and you know, the label of the data, it's two classes, you know, which has been indicated by 1 and 2. So up to point, this is 67, 68, 69. No, sir. This is 77. Up to point 77 are in class 1, and starting point 78 is in class 2. And these are all points. So I will just plot the first 77 points in different color to see the classes in different colors. So hold on and plot point 1 to 77, 1 to 77 in red. See, there is this red class inside this blue class. That's the example that we had for the motivation of kernel methods, you know, that in 2 dimension there's no linear classifier and so on. So MATLAB has built-in function for support vector machine. In your next assignment, you need to implement support vector machine yourself. You know, don't use built-in function of MATLAB. To implement support vector machine, you have to do, you just need to solve quadratic programming. MATLAB has solver for quadratic programming that you can use that built-in function for quadprod is a function in MATLAB which solves quadratic programming. You just need to give the objective function and the constraint. You can also use forgot the name. There is this tool Stephen Boyd has in his group. They have a tool that you can call it inside MATLAB for convex optimization, and it's as easy as just writing. I mean, it's exactly the same that you write your objective function and your constraint. You can write it inside MATLAB. Forgot the name of the package. Just you say begin this package and end this package, and between these two, you write just minimize this objective function subject to this, subject to that. You can use that one as well, but maybe it's in this case it's easier to just use quadprod of MATLAB. Anyway, MATLAB has built-in function SVM, train is the function. And SVM train take X as input and Y is your labels. And these parameters show plot true means that I want SVM to show the plot of data and the decision boundary. If it's false or if you don't use this, it doesn't show it. If it's more than 2 dimension, this part is not going to work. It cannot visualize. Okay, so That's basically, you know, a linear classifier that support vector machine computes for these two classes. And the data is not linearly separable, so it's quite clear that support vector machine can do any good job here. But as I told you, you know, making support vector machine nonlinear is very easy. You just need to replace all of this x transpose x's in your objective function with a kernel function. So if we do this, you know, I can add more parameters to this function. After true, I can say kernel function, so it's going to use a kernel function. A kernel function could be linear, so linear kernel function is x transpose x. So if I use linear kernel function, nothing interesting is going to happen. It's going to be linear. I mean, the result is going to be linear. See? So, but I can use other type of kernel, which is not linear, like RBF. So RBF kernel, if I use, okay, that's going to be the decision boundary. So it does very good job in separating these two classes very easily, you know, by just changing x transpose x to kernel of x. And x, and this kernel is just e to the power of, you know, x1 minus x. These points that have been, that there are circles around them are support vectors, you know. So the decision boundary depends only on these support vectors. Alpha corresponding to any other point is 0 in the dual formulation. So these points have no effect in the optimization. Only the points close to the boundary, close to the margin, are points that are important for making the decision boundary. As you can see, you know, SVM didn't do a perfect job in terms of separating this training data, and there are points that have been violated the decision boundary. And all of these points are support vectors. Okay? So there are other type of kernels that you can use. You can use polynomial kernel, for example. In this case, polynomial kernel also does a pretty good job. You know, kernel, as I mentioned in the previous lecture, is a way of measuring similarity between two set of points, and different kernels have different behavior. In terms of classification, and specifically in terms of support vector machine, 90% of the time, the best type of kernel that you can use is RBF. So try RBF first for support vector machine. Okay, let me do another example. This is 2 and 3. If you remember, we had this data set digits 2 and digit 3. And the dimensionality of the data was 64. I am going to load this data, but I'm going to compute PCA on that and map it in two-dimensional space, and then compute the decision boundary in two-dimensional space. So I remove the mean here. I apply singular value decomposition. So it's going to give me basis, and basis transpose x would be basically new data, my data in two-dimensional space. And I define labels. The first 200 digits are 2, and the second 200 digits are 3. And here is, we are running this, which is a linear classifier. So we have like class 2 and class 3, and this is decision boundary. And you can see all of the support vectors that have to do with decision boundary. Some of the points violate the boundary, but it does a decent job. If I change this to, if I use a kernel, then decision boundary will be nonlinear. See, decision boundary now is nonlinear. It's not a linear decision boundary. Okay, any question? Okay. So, a while ago, we learned about PCA, Principal Component Analysis, in this class. And we learned that we can use PCA for feature extraction. Sometimes it's useful to map the data in lower dimensional space using PCA and do the classification in that space. PCA, if you remember, captures a subspace. The assumption for PCA is that the data is close to a subspace, and we map the data or project the data on that subspace. What if the data is not linear? What if the data is close to a submanifold of the space, not subspace? There are many different techniques to handle this problem, and we are not going to go through the detail of that, but I'm going to mention a simple extension of PCA which can take care of this nonlinearity through the concept of kernel that we just learned. So we can kernelize PCA and make kernel PCA instead of PCA, which can take care of nonlinearity in the data. So let me remind you that PCA, when the data is centralized, you can compute the covariance, which is X transpose. And when you have the covariance, you can do eigendecomposition on covariance matrix. And then U will be your basis, principal components. U transpose X is your mapping in lower dimensional space. You can reconstruct point by just the same projection matrix, the transpose or the inverse of this projection matrix. And you can map a new data point, which is not part of the training set. You can do out of sample, and you can reconstruct out of sample. This is direct PCA algorithm that we have seen before. But when you have X centralized, then you can do singular value decomposition on X, and U will be your principal components. U is eigenvectors of X, X transpose. And V is eigenvectors of X transpose X. Okay? So X is a D by N matrix. So in the case that D is small and N is large, here we need to decompose a D by D matrix, and if D is smaller than N, then it's more beneficial to decompose this matrix. Here X transpose X would be N by N matrix. But you can imagine, a case that N is smaller than D. The number of data points is less than the number of dimension. recently, the type of data that we have are quite high dimension. We are working with images, we are working with gene expression data. Gene expression data, you have genes, expression of genes, which is a few thousands, and you have only 100 patients. So the number of data points is 100, but this is few thousand. So X transpose would be a pretty large matrix to decompose. But this is 100 by 100 matrix to decompose. So computing, in this case, computing V is easy, computing U is hard. Can we get rid of computing U altogether and just compute V? You can see that according to singular value decomposition, X is U sigma V transpose, means that there is a relation between V and U sigma and X. So it means that U can be computed based on X, sigma, and V, right? Even if I don't have it. So X is U sigma V transpose, and V is orthonormal. It means that XV is U sigma. And it means that XV sigma inverse is U. So even if I don't have U, even if I haven't decomposed X transpose and I don't have access to its eigenvector, knowing the eigenvectors of X transpose X, which is V, and singular values, which, this sigma can be computed based on eigenvectors of X transpose X or X transpose, makes no difference, right? So just by decomposing X transpose X, I do have sigma and I do have V. So I can compute U. So if you take this direct algorithm and replace all occurrence of U here with this form, then you come up with a dual form of PCA that does not depend on D, but depends on N. And doesn't need to decomposition of X transpose, covariance matrix, but it can be done by decomposition of X transpose X. Okay? Let's see, for example, you want to map the data in lower dimensional space. You have to, in direct PCA, I have to compute U transpose X. I need to compute U transpose X to go to lower dimensional space. But look at this U transpose X. If I multiply U transpose here and multiply U transpose here, what this right side is going to be? It's going to be sigma V. So U transpose X, which is my mapping in lower dimensional space, is just sigma V. So I don't need to know U. I can compute it by sigma and V. So I can compute it by decomposition of X transpose X. Or say, for example, I want to reconstruct a point. Reconstruct the point is U transpose is U transpose X. Okay? And U is X, V sigma inverse. And U transpose is sigma inverse, V transpose, X transpose. Okay? Times X. Then you can simplify this and see that everything basically can be written in terms of U and sigma. This is the relation that we have based on singular value decomposition. And we can write XV equal U sigma, or we can write U is equal XV sigma inverse. And if you replace this in algorithm 1, you can come up with this algorithm. embedding in lower dimensional space could be just sigma v transpose. Here, to compute, reconstruction, which is u y or u sigma v transpose, I'm going to have x v sigma inverse sigma v transpose, which is x b v transpose. These two will cancel each other. You can encode test example, and you can reconstruct test example. Just by replacing this formula in the direct formula. So this is dual PCA. In dual PCA, I don't start with the composition of XX transpose. I start with the composition of X transpose X in a step. So I have, if in the case that n is small and d is large, it's more, economic to do this, to do it this way. But this is going to suggest, a way of making this algorithm nonlinear as well. Do you see how? Based on what we learned in support vector machine, the way that we kernelized support vector machine and made the decision boundary nonlinear, can you see how can we make this nonlinear? The idea in support vector machine and make it nonlinear was that, or the idea of kernel method, was that if you can recast your problem in a way that it does not depend on the coordinate of points, but it does depend on the dot product, inner product between points, then we are done, right? Because you can replace each x by phi of x. You don't know phi, but when you have phi of x transpose times phi of x, you can replace that with a kernel. So what can I do here to make it nonlinear? Yes?
When you compute x transpose x, you just replace it with the kernel value rather than the dot products?
Exactly, yeah. Yes. I start with x transpose x, right? So suppose that data in the original space is not close to a subspace, but is close to a submanifold of the space, right? My assumption is that if I map the data in higher dimensional space, the data, I can use this bliss of dimensionality in higher dimensional space. My data has sort of linear structure. Okay, so basically I'm going to map my data to higher dimensional space, phi of x. So I start with x transpose x. So if all of the data have been mapped to higher dimensional space, that's going to be phi of x transpose times phi of x. But phi of x transpose times phi of x is a kernel. So I can start with a kernel. I can decompose this kernel, which is n by n matrix. I can decompose this kernel. Okay? For example, it's n by n matrix. And Kij, for example, is just e to the power of xi minus xj squared divided by some parameters. So similarity between 2 points. So here we can start with some kernel. But okay, I would like to map them in lower dimensional space, then I would like to reconstruct them to map them in lower dimensional space. If I have sigma and I have v of this kernel, then I can map them in lower dimensional space. So as if I'm mapping, a nonlinear structure in lower dimensional space. As if I project everything in this nonlinear manifold, and then I unfold it and show it to you in a two-dimensional, or I mean lower dimensional space. Okay. So the idea of kernel PCA, as I explained, is that you map your data through function phi to a higher dimensional space, to a Hilbert space. And so basically, X has been mapped to this space. And then we do PCA on this space. We do PCA here. But to do PCA here, if I want to do direct PCA, I need phi of x. But I don't have access to phi of x. I cannot compute covariance matrix here. Because covariance matrix is phi of x times phi of x transpose. I don't have it. But if with dual PCA, I don't need to compute phi of x transpose. I need to compute phi of x transpose phi of x, which is inner product. And I do have inner product, which is kernel. Okay? So I compute a kernel, and then I go for everything. So let me show you that here, basically, we have a kernel, which is phi of x transpose times phi of x, or which has been defined this way. And then just everything is going to be PCA, a dual PCA. So I have phi of x transpose phi of x, which I do eigen decomposition on that, and it's going to give me V, and it's going to give me sigma as well. I would like to map the points in lower dimensional space. It's going to be simply Y transpose phi of x, which can be written in dual form as sigma V transpose. Okay? And I do have sigma and V transpose. There are eigenvalues and eigenvectors of this V, this K, kernel matrix. Okay, so suppose that I want to reconstruct training data. X hat was U, Y. In dual form, it was U sigma V transpose. And you can, I don't have U because U is eigenvectors of like phi transpose, that I don't have it. I have to rewrite everything in terms of V. And if I rewrite everything in terms of V, I come up with phi of x V transpose. So I can't do reconstruction in kernel PCA. So if I do kernel PCA, I can map points in lower dimensional space. I can't map it back. I cannot reconstruct them. Because the reconstruction depends on phi of x. To do reconstruction, I need phi of x V transpose. But I don't have phi of x. Okay? So we never explicitly computed phi of x. So we can do reconstruction in kernel PCA, but we can map it in lower dimensional space. We can do out of sample. So for out of sample, it's just simply you transpose phi of x, a single point, which is in dual form. It's sigma inverse V transpose phi of x transpose phi of x. This is kernel, so I can compute it. That's fine. And this capital X, this is a small x. This small x is a single data point. This capital X is a whole data point that you had your training. The small one is out of sample. So x capital X is d by n, all of the data points that you have, and lowercase x is just a new vector, and you want to embed this. It's out of sample. You just need to compute kernel of capital X and lowercase x, means that you need to compute similarity between all of these n data points and this new data points. It's going to be a vector of length n, right? I have n data points here, and this is just a vector of length and similarity of each of this data point when this new one. Similar to the second data point with this new one, similar to the last data point with this new one. It gives me n similarities, so it's a vector of length n. Okay. Reconstruction of test examples we can do. Again, we cannot do. So it's not as powerful as PCA in a sense. We cannot do reconstruction. Okay. So there is one more technicality to do PCA. If you remember, in PCA, we assume that the data has been centered. You know, we take the mean of data out first, and then we compute XX transpose or compute X transpose X, and so on. So based on this assumption, the mean of this phi of xi should be out, you know. It should have 0 mean. But we never computed phi of x. We don't have it explicitly. How can we centralize something that we don't have? Basically, we don't need to centralize phi of x itself, you know. We would like to compute phi of x times phi of x transpose. I need to compute phi of x transpose times phi of x. All of my derivations and my calculation are correct if this is centralized. So what at the beginning, we don't know that if it is, right? In fact, you know, what I have to compute is phi of x minus the mean of this transpose times the same thing, you know. That's the kernel that I have to compute. You can show easily that this kernel is basically, you know, this tilde kernel, which is the original kernel minus these two terms and plus this term. So it's basically it means that you want to have a kernel corresponding to centralized phi, compute your kernel first, which is kxy, compute your kernel first. And then this basically means that take the average of all of rows, subtract. Takes the average of all of the columns, subtract. Takes the average of columns and rows, add. You can prove that this is corresponding to basically this computation, that assume that there is a phi tilde x that's phi x minus the mean of x. And in fact, what you need is phi tilde x times tilde y, say for example, for two different x and y. So you need this term transpose. I forgot the transpose here. You need this term transpose, that's the time this term. It's going to give you phi x transpose phi y, which is just a kernel. You're going to have phi x transpose expectation of phi y with respect to y, which is basically expectation with respect to y of the kernel. And you're going to have expectation with respect to x of phi x times phi y, which is simply expectation with respect to x of this kernel. And then you have a term which is expectation of phi x transpose times expectation of phi y transpose, which is expectation of kxy. So you just need to compute the kernel and then center it this way. And then you can do PCA on that. I mean, you can do the eigendecomposition on that. And this will take care of nonlinearity. Any question? Okay, the last advice actually that I can give you about kernel PCA is that never use kernel PCA in practice if you want to map nonlinear data to lower dimensional space. It's not going to work well. I mean, theoretically it's interesting, but if you use just you know, out-of-the-shelf kernel like RBF kernel, put it here, like RBF do excellent for classification. But you want to do dimensionality reduction or feature extraction, use like RBF here and map the data in lower dimensional space, it's not going to be really useful most of the time. So there are many other techniques for dimensionality reduction, like LLE, like local linear embedding, or isomap, or LTSI, and many other techniques. All of why I presented kernel PCA, because it's a simple extension of PCA, and also it can be shown that all of those techniques are in principle kernel PCA. But they compute different kernels. The kernels is not just RBF kernel. It's a data-dependent, data-driven kernel that you have to run an algorithm to compute it. It's a way of finding similarity between points, but not finding similarity as easy as e to the power of xi minus xj. You need to run an algorithm to find how similar these 2 points are. And LLE computed in one way, and isomap computed in another way, and so on. Okay? So they compute this kernel in many different ways, but at the end of the day, they come up with n by n kernel matrix, and they do decomposition on that, and then they map it on lower dimensional space, and so on, exactly the same that we explained here. Some of them are even more restricted. If you do LLE or isomap, you cannot even do out of sample points, that you can do for kernel PCA. Maybe I can explain the idea of, the insight of isomap to you just very quickly. If you have, if I can borrow, a piece of paper. Thank you very much. This is linear, right? But suppose that it's nonlinear. It's a submanifold like this. The idea of isomap is that, okay, now the Euclidean distance between points is not, doesn't explain the geometry of the points. If points are far apart on the manifold. If points are close by, that's okay. If I choose this point and the point right beside it. The Euclidean distance is a good indication of geometry. But if I point one point here on the manifold and another point here. Sorry. This is one point on the manifold. This is another point on the manifold. The Euclidean distance between these 2 points, is just this short line, right? It's not good indicator of the geometry of the data, because really this point is not close to this on this manifold, on this manifold is far apart. So the intuition, the insight of basically isomap is that replace geodesic distance with Euclidean distance. So Euclidean distance is just this short distance here. Geodesic distance is distance between these 2 points on the manifold. So they approximate this distance, and there are classical algorithm to compute this distance, like shortest path between, if you make a graph out of this, you can find short spanning tree, and you can find short, but these are classical algorithm basically in graph theory. You can approximate this distance, and then you can come up with n by n distance matrix such that each element of this matrix is geodesic distance between 2 points rather than Euclidean distance between these 2 points. And when you have this, you can make a kernel out of this easily. You just compute, this is a constant kernel matrix, which is just centering matrix. And this is going to be a kernel. And then they replace this kernel here, and they do basically, eigen decomposition. There's also, another technique, which is there are a set of techniques which try to learn this technique. You know, they run an optimization problem to compute this kernel instead of using out-of-the-shelf kernel or running an algorithm too. Okay. Okay, let me show you yet another extension of PCA, which is supervised PCA. You know, we are doing classification, and we would like to map the data in lower dimensional space for the purpose of classification. Okay? So in PCA, we never use the label of the data. When we map the data in lower dimensional space, we never map the label of the data. In FDA, we did, for example. You know, I gave this example to you when I wanted to motivate the lecture for FDA, that you have these two classes, and this is going to be PCA, and if you map your data along this line, then it's not going to give you a good separation, but FDA is going to compute this, which is going to give you a good separation between these two set of points. Okay? Now, in general, actually, we may want to map the data in lower dimensional space according to different target values. You know, if I show you this data point, you can put them in two different classes this way. So some people have glasses and some don't, right? And the same data set, I can put it in two classes this way, or two clusters this way. Some people have beard and some people don't. Suppose that I want to do classification for glasses. I want to classify those people with glasses, compared to the case that I want to do classification for beard. So most likely, I need two different mapping of the data in lower dimensional space. One of them needs to be, you know, have a good indication or be separable for beard, and the other one for glass. Okay, so that's what PCA does. PCA is blind with respect to labels. But if I want to do glasses versus no glasses, I can do supervised PCA and come up with this mapping that gives me a very good you know, distinction between these two classes when PCA doesn't. Or I want to do beard, you know, I can map it this way. But as I said, PCA is blind with respect to the direction of variation which is in my mind for classification. I want to guide PCA towards the direction of variation that I have in mind for classification. Okay. So this is basically the formal problem statement that we are trying to solve. You know, we have a set of data xy, and x is from RP, is p-dimensional data, and y is from RL, is L-dimensional data. And this is usually in classification one-dimensional, and it's categorical, but the setup of the problem is more general. You know, assume that y is L-dimensional, and doesn't need to be categorical for example. You know, could be real value, it could be anything. So, so given n of these data points, IID, we would like to map this data point in lower dimensional space. You remember that in PCA, we had this transformation matrix U transpose that maps everything to lower dimensional space. We had this U transpose X. So we are going to have U transpose X map everything to lower dimensional space. But I want this lower dimensional space to be a good representative of Y. Y is my label. I want U transpose X to be good representative of Y. So one way to make sure that it's good representative of Y is to make sure that dependency between Y transpose X and Y is high. You know, just think of X as random variable and think of Y as random variable. And I do U transpose X. I want U transpose X to be dependent in Y. Dependency between these two, I want to be high. Okay? So in literature, there are many different techniques that somehow try to do this. And we learned about FDA, Fisher-Disker analysis. There are a class of techniques, not just one technique. There's a class of algorithm. It's called metric learning that try to do something similar to this. And there are a class of techniques which is called sufficient dimensionality reduction algorithm. They also try to do the same things. And there are some individual techniques like this technique by Tipshrani and his group that somehow try to do this. So in metric learning, usually we are trying to compute, Euclidean distance between point xi and xj is just xi minus xj squared, which is xi minus xj transpose xi minus xj, when xi and xj's are vectors. That's Euclidean distance. So in metric learning, we are trying to compute a Mahalanobis distance instead of this Euclidean distance. So basically, we are trying to put a matrix A, which should be positive semi-definite matrix here. If it's a positive semi-definite matrix, it means that it can be decomposed to two matrices, U transpose U. And then I can take this U inside. I can write it as UXI minus UXJ. And I can write this as, U transpose. And I can write this as U transpose Xi minus U transpose Xj. Okay? So basically, metric learning tries to implicitly compute U transpose X, tries to map the data points in another space, such that similarity between points is more indicative for the purpose that we have. You want all points with beard to be close to each other. You want all points with glasses to be close to each other. Map them in another space such that all of the faces with beard are close, their distance are close, and if someone has beard and the other person doesn't have, they're far apart. Okay? And in sufficient dimensionality reduction, actually, they're basically trying to compute this dependency in a way. Let me skip this couple of slides and emphasize on basically what we want to cover. There is a notion which is relatively new. It's called Hsic. Hilbert-Schmidt independence criterion. It's a way of measuring dependency between two random variables. Okay? And it's based on the kernel concept that we just learned. I skipped the mathematics of Hsic itself and just try to drive supervised PCA. But instead of the mathematics of Hsic, I just try to explain it very intuitively. If we have time later on, we get back and show you, what's the mathematics behind Hsic. Since people learned about the concept of kernel, there are all sorts of algorithms that try to make a linear algorithm nonlinear, just simply by mapping everything to a higher dimensional space and recasting the algorithm in a form that doesn't depend on the coordinate, but it does depend on the dot product between points. But there is a new line of research which tries to kernelize these concepts, not just the data, So we can compute correlation easily. But we can't compute dependence easily. Correlation means just a linear dependency, which is easy to compute. But it's not easy to compute the dependency between two random variables, because it could be any sort of dependency. It could be nonlinear. Maybe y is x squared, maybe it's x cubic, maybe it's sine of x, maybe it's cosine of, maybe it's a completely unknown function. Which one you are going to test, to see if they have this type of between these function and this state function and this state has any correlation or not. Basically, dependency means correlation between all possible bounded functions over these two variables, right? Now, get back to the idea of kernel. In kernel, we said the data here is nonlinear. In higher dimensional space is linear, right? So let's do the same thing. Data here have some sort of dependency in some sort of nonlinear form that we are not aware of. Let's map them to high dimensional space. Hopefully everything would be linear there. And if I compute correlation in high dimensional space, it's as if I computed dependency in the original space. Basically the assumption is that there's a Hilbert space that I can map all of these x's to this Hilbert space and all of the y's to that Hilbert space, and then look at the dependency between mapped point there, and then decide about dependency of the points there. To decide about correlation, I can, for example, look at the norm of covariance matrix in original space. So if they have moved to higher dimensional space, I can extend all of this concept. I can define operator, like covariance operator in some Hilbert space. And then I can compute the norm of this covariance operator. But in this Hilbert space, we cannot compute Frobenius norm. We can compute Hilbert-Schmidt norm there. And Hsic is basically the norm of Hilbert-Schmidt operator in higher dimensional space, which is an indicator of dependency between two random variables. Okay? So if we have time later on, we will see the exact mathematics behind Hsic. But what we need today is that end of the day, when you do all of this math, empirically, you can compute the dependency between two random variables as trace of K, H, L, H. Okay? When K is a kernel over random variable X, and L is a kernel over random variable Y. Okay, suppose that I have two random variables, X and Y, and I would like to find dependency between these two, and I have n samples from random variable X, and I have n samples from random variable Y. Then I can make a kernel over these samples, which is n by n, and I can make a kernel over these samples, which is n by n. Okay? Then I can compute basically this trace. And H here is a constant matrix, which is I over 1n E transpose, and E is just 1, 1, 1, 1. This is a constant matrix. It's identity minus 1 over n E transpose. And E is 1, 1, 1, so E transpose would be n by n matrix full of 1. So identity minus 1, 1, 1, 1, 1 when it has been divided by n, number of data points. So this is a centering matrix in a sense that if you compute X, H, it's as if you have removed the mean of X. Okay? So when you have HLH, it means that L has been double centered, you know. Mean of rows and mean of columns have been removed. Okay, so this is Hsic. So you have samples from this random variable and you have samples from this random variable, and you can put it here and compute this trace. If it is 0, means they're independent. If it's more than 0, means these two random variables are dependent. And there's no upper bound for this. You know, it could be as big as you want, but it's always positive. Okay? Okay, so now what's the idea of supervised PCA? The idea of supervised PCA is that I have X, and I want to map X in lower dimensional space, but I want to map it in a way that it has maximum dependency with Y. To make sure that it has maximum dependency, we are going to use Hsic as the measure of dependency. So I have X. X will be mapped to lower dimensional space, and I have some Y. Okay. And I want Y transpose X to have maximum dependency to Y. Or I can keep it general, and Y could be, you know, also a matrix. And assume that we have n data points here. These are n labels. These are n, you know, observation. Okay, so if I compute a kernel over X, I compute a kernel over Y, and put it here, then I have dependency between these two, right? Now, suppose that I mapped everything through U, and I have U transpose X. Make a kernel over U transpose X. Make a linear kernel over U transpose X. What would be a linear kernel over U transpose X? Linear kernel over X is what? It's X transpose X, right? Linear kernel over U transpose X is? Sorry? I can't hear. It is sine of U transpose X divided by cosine of X transpose U times tangent hyperbolic of U. Is that right? It's not? So what is it? You know, it's simple. You know, I have X. X transpose X is a linear kernel over X. I have U transpose X. What's linear kernel? Yes, it's U transpose X transpose times U transpose X, which is X transpose U, U transpose X. So that's a linear kernel over U transpose X, right? So this is K. And I have Y, and I can compute a kernel over Y. Any kernel, you know. Just call it L. For X, I computed kernel over U transpose X. For Y, I just compute any kernel over Y and call it L. Now, if I want to compute the dependence between U transpose X and Y, don't forget that the goal was to maximize the dependence between U transpose X and Y. If you want to maximize the dependence between U transpose X and Y, you have to maximize trace of KHLH when K is X transpose U transpose X H L H. You know, everything here is known except U. You know, X is known, H is a constant matrix, L is a kernel matrix that you computed for Y. The only unknown is U, so I would like to compute U to maximize this trace. Okay. You know, I can, it's trace, so I can rotate everything. You know, I can put this H here, or I can put this L here, and I can put, what was H? Or I can put this X here, or I can put this U transpose here. You know, all of these traces are the same. So basically, I need to maximize trace of U transpose X, H, L, H, X transpose U. Okay. You know, we have a problem similar to the problem that we had in PCA. That if you remember in PCA, we had 2 degrees of freedom. One was the direction of U, and the other one was length of U, you know. We could choose U arbitrarily large in terms of length, which could, you know, make our objective function large. We have the same problem here. You know, U here is a matrix, but, you know, suppose that you want to map everything to one direction, a vector. This doesn't have any upper bound, you know, because this U could be as large as you want. It has no upper bound. You have to restrict it the same way that we did this restriction for PCA. So in PCA, if you remember, we had a restriction that U transpose U, the length should be 1. We put similar restriction here. This is matrix, we put U transpose U is I. Means U has different vectors in it. U transpose U is I. Means they're orthonormal. Means that length of each of them is 1, and they're orthogonal to each other. Okay, so I have to maximize this. And X, H, L, H, X transpose is a noun. Trace of U transpose, a noun matrix U subject to the constraint that U transpose U is identity. Okay, do you know how we can do this? You can do Lagrangian, right? But if you write Lagrangian and take derivative, set it to 0, you know what's going to be the final solution? Because it's a very classical problem in optimizing trace. I mean, in many handbook of matrices, you can see the solution of this optimization. It's eigenvectors of this matrix as a solution, corresponding to maximum eigenvalues. Okay, so U will be eigenvectors of X, H, L, H, X transpose. if U is say, for example, if it's P by D, D is dimensionality of your original data, P number of principal or number of bases that you want to map your data to. Then we need to choose the eigenvectors corresponding to the top P eigenvalues. So simply, you need to compute this matrix and find the eigenvectors. Okay, that's going to be principal component. That's going to be your basis. So this is supervised PCA. Then you can map your data in lower dimensional space. You can compute U transpose X. This U transpose X in PCA, when you had this U transpose X, the first principal component was direction of maximum variation. Now the first principal component here is the maximum, is not the maximum, the direction of maximum variation. Is direction which is aligned to your label, has maximum dependency to your label. So it's good for classification if you have these labels. I told you H is centering matrix. So XH means X when you remove the mean of X. And X transpose is just a transpose of this because H transpose and H are the same. So it's X when you remove the mean of that times the transpose of X. Okay? So X minus the mean of X times X minus the mean transpose. What is this? It's covariance matrix, right? So if I replace L with I, this is covariance matrix and the solution is PCA. But if I put L here, it's supervised PCA. So it's just a general form of PCA. You can think of I, identity matrix, as a kernel over labels. What type of kernel it is? It's identity matrix. It's 1, 1, 1, 1, and 0 everywhere else. And kernel is supposed to show similarity between points, right? It's basically a kernel which tells you that this point is similar to itself. But I don't know about any other point. As if I have no information about the grouping of the data. As if I don't have any label. When I have no label, I know this point is similar to itself. That's the only thing that I know. I don't know about grouping. But if I tell you labels, all of these points are digit 2. All of these points are digit 3. Then I have more information. Each point is similar to itself, but this point is also similar to this one. This point is also similar. This point is also similar. Then you have a kernel over Y, which shows the similarity between this point, and you replace it here. So it's a generalization of PCA that if you put identity matrix here, it's going to be PCA. If you put, if you use the information that you have about label, then it's going to change the direction of this subspace towards the direction which maximizes the dependence with labels. And it's quite useful in classification, For feature extraction, it's pretty useful algorithm. It can be kernelized. I will show you how it can be kernelized. And in contrast with kernel PCA that was not useful, it's very useful. Kernel supervised PCA is very useful for classification and can basically find very useful features for classification. Any question? Yes? Sorry?
L is not a kernel function, right? It's something that you place with your data, right?
L? L is a kernel function over your label.
Over your label.
Yes.
You know the labels of your data, right?
Yes, you do.
Create a kernel function to map that.
You have n data points. You have n data points. Say this is my y. 1, 1, 1, 0, 0. I have 5 data points. I can make a kernel over this. For example, it could be any different kernel, any type of kernel. If I make a Dirac kernel, for example, then I have data point 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. It's going to give me a block here of ones. And a block here of ones, 2 of them. For these 2 and these 3. So it's going to tell me that these 2 points are similar, and these 3 points are similar, and these points are dissimilar. Or these points are dissimilar. That's one type of kernel that you can make. But you can make other type of kernels as well. Yes?
So if we only have 2 classes, then kernel doesn't really matter too much. But if we have more then does choosing the right kernel becomes more material?
Even for 2 classes, it's important. But for any number of classes, you can compute a kernel of this form.
But kernel, in a sense, is comparing the similarity between points, right?
Yeah.
So if we have, say, 3 classes, then how come the class 1 is closer to class 2 then?
If 2 points belongs to the same class, it's 1.
Yeah.
If they belongs to different classes, -1.
It's always.
And it should be also normalized. It's 1/3, it's 1/2, -1/2. But yeah, it could be any kernel, including this one. This one actually is pretty good for labels.